No, that's good. Very clear. It's
Understand a little bit
impossible.
more about my
Yeah.
equation.
Every time I learn more. So when is it gonna be this?
We'll start on Monday, and we'll have it in the afternoon after the lectures, before the dinner. Almost every day for the
For 2
last
weeks.
2 weeks.
I see.
Yeah, we have 30-something people already signed up.
How much time will you give to every student?
7 minutes
7 minutes.
plus questions.
How generous.
There's so many of us, so it would be hard to manage otherwise.
Sure.
I want to make it easy to prepare as well.
Right. Is it gonna be blackboard also?
Well, we say we encourage blackboard talks, but anyone who wants to use transparency as well.
Okay. So yeah, I think we're gonna start. So if you wanna learn about Mellin amplitudes, you should come. What is your name? Arash. Nice. Where are you from? Sorry?
Iran.
Iran. So you always eat this Persian food,
Yeah.
the best food in C4C?
I love it. May I go ahead now?
Sure, if everybody is in here.
Yeah, so as people are getting in, I wanted to make a quick announcement about the student talk. You probably know we are starting on Monday. We'll have the talks in the afternoon before the dinner. Maybe some downside to it, but nice thing is we'll get to chat with the students over the dinner. And there are, as of right now, 6 empty slots. So if you receive the email, please go sign up in the Google Sheet. If not, please contact Pedro, Nima, or me. We'll write your name in the Google Sheet.
Thank you. Okay, so in this last lecture, I just want to conclude this discussion that we were having about finite temperature. And then I changed my plan because I realized that really most of you already know all of these basic things about AdS CFT. So today I will talk about Mellin amplitudes, which I think will be probably more interesting for you. So, but before that, I will just conclude this discussion of CFTs at finite temperature. So we already discussed last time that just by dimensional analysis, the entropy density must be proportional to the temperature. So here I'm doing the case where I have flat space times the time circle, okay, with some period beta equal to the inverse temperature. So the only scale you have available is the temperature, and so the entropy density has to be proportional to temperature to the d-1 with some coefficient, which again, you can think of this coefficient as some measure, so of the number of degrees of freedom on your theory. Okay. Again, I don't want to say that this is a measure in the sense that it always a quantity that always decreases under RG flow. That is not true, but physically it's clear that if you have a higher entropy density, you have more degrees of freedom. Okay, so it's a good measure just in that sense. So, and we saw that if we start to put a gas of particles in AdS, we get the wrong scaling, right? So that does not give the correct scaling for for a CFT in the dimensions. So what we need to do is now to put gravity, and the actual gravity dual of this is going to be a black hole. And in fact, since we are taking this flat geometry, it's going to be a black brane, like Simon was mentioning. And so the metric can be written as well, here this I and j is just the spatial directions of your so d minus this rd minus 1, where this f of z is just 1 minus we can write it as zh over z to the power d, if I'm not mistaken. Yes. Okay. So as you can see, this is a black brane geometry. So when z is equal to zh, you have an horizon. And now you can compute the entropy density just by measuring the Bekenstein-Hawking entropy of this horizon. Okay, just the area of this horizon. But okay, before doing that, you have to relate it. Maybe I can continue here. No, I shouldn't. Let's keep to the rules of Blackboard use. So regularity of that geometry implies that you have to fix this periods of the time coordinate. So you should do this exercise and show that this Euclidean geometry, it's only regular, so it doesn't have a conical defect when z is equal to zh, that around that point, if you choose the period of this Euclidean time circle to be given by 4 pi zh over d. Okay. So this, of course, is just 1 over the temperature, the period of your time circle. And now, of course, you can compute the entropy of your black hole. So this is just the area over 4g, g Newton, which if you go back to my notations, you should write like as 4 pi over L Planck to the d minus 1 times the area. So what is the area? Well, we just look here. It's r over zh to the d minus 1 times the area along the, just the volume of the flat direction, this flat space. So the entropy density, so you get that the entropy density is some, well, I can write it, but okay, 4 pi. So you just replace here what you get. Essentially, you get t to the d minus 1 with some specific factor here, right? So whatever, you have to replace it. zh, 1 over zh is 4 pi over d to the d minus 1. And of course, you get this r over L Planck to the d minus 1. Okay? So I should write it like that. T to the d minus 1. Okay? Okay, so first conclusion is that you get the right scaling. And second comment is that you get a specific value for this constant Cs, which in particular, it's very large in the semi-classical limit. So it also scales with this parameter that we were relating with n squared. So in particular, if you take the ratio Cs over Ct, this is given by some function, so some universal function that only depends on the space-time dimension, right? So this is what gravity tells you. And so, okay, so what's the physical meaning of this equation? The physical meaning is very simple. So Ct measures the 2-point function of the stress tensor, okay? So measure just g Newton directly from the action by just graviton propagation. Okay? While CS measures the entropy of black holes, okay? The high energy density of states. So it measures g Newton coming from the formula, the Bekenstein-Hawking formula. Okay? So the fact that this formula is universal is just the fact that if you know that you have a gravity theory with some g Newton that you can measure by just graviton scattering at low energies, given that you know g Newton, you already know that the high energy density of states is controlled by the same number. Okay? So gravity has this interesting fact that if you know some low energy data, you immediately also learn something about the very high energy density of states. Okay? So, of course, if you take a given any CFT, this is not true. Okay? So this is not universal in a generic CFT. So one natural conjecture would be to say, if I assume that I have large n, so some CFT with large n and with large gap, this delta gap that I was discussing yesterday, can you prove that these two conditions imply this universal ratio? Okay? So this would be another natural conjecture like I was discussing yesterday. I should make two comments. So one comment is that in d equals 2, this is automatic. You don't need any constraint. Any CFT in d equals 2 will just satisfy this universal ratio immediately because both these numbers are just the central charge up to some number. Okay, the central charge of the 2D CFT. And the other comment is that if you look in Super-Yang-Mills, this ratio works if you go to strong coupling. Okay, so when you go to lambda to infinity, so as it should, because then you have a large gap, so it should work. But it does not work at weak coupling, but fails just by a factor of 3/4. Okay, the famous factor of 3/4. For those of you who remember some of this history. Okay, for the ones who don't, is that in the early days of AdS CFT, people were computing this at weak at strong coupling, and they found this mismatch by 3/4. And at that time, at least for some people, it's not completely obvious that things could change with the coupling. Some quantities were matching on the nose, some depending on the coupling. And if something looks almost the same, it only fails by 3/4. You gotta get a bit confused. Maybe you are just doing a mistake or something. But now it's clear that it's just evolves with the coupling, but it varies very little, this ratio in Super-Yang-Mills from weak to strong coupling. Okay. Any question about this?
That universality is when you've got Einstein gravity coupled to whatever matter you want?
Yes. Einstein gravity, exactly. Higher curvature corrections will change this, exactly. Yes, so that's precisely the same idea that this gap should be suppressing the size of higher curvature correction. Any other question? Okay. So Mellin amplitudes. What are Mellin amplitudes? So these are just a particular representation of conformal correlation functions. Okay. So I'll just write. Now you already know this embedding notation. So I'll just use it. So let me take scalar primary operators. Let me take this endpoint function, and I'll write it in the following form. I'll write it as some integral. I'll explain. And then m of these variables Okay, so let me explain this formula. So this is the formula. It's just an integral representation, and this function m is what I will call the Mellin amplitude. So what am I writing here? So you have this dependence on the positions of the insertions of the operators, and all of that dependence is put here. So remember that this is just the distance square if you go to the Poincaré patch, for example. Okay? So this, of course, only depends on the distances between the points. It's a Poincaré invariant correlation function. So there you are. And you just raise that to some powers, and you integrate over these powers. Okay? So the gamma functions are just there for convenience. You will see later that they make some things more simpler. So what else should I say? So clearly, we need to impose an extra constraint. Can anyone tell me about that? What is not what symmetry of this correlation function is still not automatic in this formula? Scaling, right? So each one of these operators is an homogeneous function of the point of scaling of this embedding point P. So we have to impose that. So let's do that. So if we scale Pi, we just get a power there, which is gamma ij summed over all j from 1 to n for j different from I, right? And this must be equal to delta I. If we impose all these n constraints, then everything is automatic. Okay, so this integral is over this constraint surface. Okay, so I will use a convenient notation. So I will define this delta I to be minus gamma II. Okay, so this diagonal gamma variable doesn't appear in the integral, so I can call it whatever I want. So I'll just define it to be that, such that now the constraint is just a sum equal to 0 without the difference. Okay, so this is just a trivial trick. And of course, I'm thinking about gamma ij as a symmetric matrix. Yes. M is the Mellin amplitude. Okay, think of it as a Fourier transform, right? You have some function of x, and now you have some function of these gammas, just some integral transform. Okay, what else should I say? So, for example, for 2 and 3 point functions, this should make sense. Okay, so this should, at least in those cases where this is trivial, this should work. And actually, if you come here, so you have these n constraints. So how many integration variables, how many free variables do you have? So the number of independent gamma ij's is n minus 1 over 2 minus n constraints. So it's n minus 3 over 2. Okay, which, if you remember, is also the number of cross ratios in an endpoint function. Okay, so we're good. We have one integral per cross ratio. And in particular, for 2 and 3 point functions, there's no integration variable. So this formula just gives you what it should. Just gives you the form of 2 and 3 point functions in conformal invariant structure. There's no integral to do. Okay, so n equals 4. The 4 point function is the first time you have to do an integral. So let me explain the integral, and in particular the integration contour in that case. Okay, so let's do this example of n equals 4, and let's take all operators to be the same. Okay, so delta I, they are all the same, equal to delta. So in this case, you can just solve this n constraints very easily, and basically what the constraints tell you. So these constraints tell you that gamma 1, 2 is gamma 3, 4, gamma 1, 3 is gamma 2, 4, gamma 1, 4 is gamma 2, 3, and the last constraint, you can think of it as gamma 1, 3 plus gamma. Okay, let's make it order 1, 2, 1, 3 plus gamma 1, 4 equals delta. Yeah? That's actually it's the first constraint directly from there. Okay, so then let me write the integral very explicitly. So this 4-point function will be given by. So I will use as independent variables, so let me leave here some space, gamma 1, 2 and gamma 1, 4, and it's okay. So m will be a function of the independent variables. After I solve the constraint, I have two variables, get from those formulas. And now I have the gamma functions, which form squares in this case. So I solve for gamma 1, 3, delta minus gamma 1, 2 minus gamma 1, 4. Unfortunately, okay. And what happens to the space dependence, right? The most important part. What happens to it? So once you solve the 6 gammas that you had here, the 6 variables, in terms of the 2 independent ones, they naturally organize in cross ratios. Okay, so basically you just left out here with minus 2 p1 dot p3 to the delta, and sorry, let me introduce, otherwise I'll be writing this all the time. So let me define pij to be minus 2 pi dot pj. Okay. So this is p13, p24 to the delta, and the rest of the dependence, I don't have space here, sorry, so I'll write it here. You just get u to the minus gamma 1, 2, and v to the minus gamma 1, 4, where, well, maybe you still don't remember, I'll write it here. So this is p13, p14, p12, p34, and v, the other cross ratio, is p14, p23, p12, p34. Sorry, p13, p24. Okay, so it's a very simple. If anyone is confused with this step, please ask me. Okay, good. But now I have to explain this integration contour. So what is this integration contour? So let me look in this complex plane, for example, of the variable gamma 1, 2. Okay? So some functions, for example, the gamma functions immediately give you some singularities. Okay? So in this case, I'll have double poles at the negative integers, 0, minus 1, minus 2. And then you have this other gamma function, for example, that also gives you poles in gamma 1, 2. But now, well, I'll just write generically here. So the first pole, let's say it's at position delta minus gamma 1, 4, and then plus integers. Okay, so of course the gamma functions always give you a semi-infinite sequence of poles. Okay, and the claim is that the Mellin amplitude will also give you the same type of poles. I will argue for that afterwards. But so the prescription for the contour is that the contour runs parallel to the imaginary axis, separating this semi-infinite sequence of poles. Okay, if you have a semi-infinite sequence to the right, you pass to the left of the first pole of that, and vice versa. Okay, so I'll just write here minus I infinity to I infinity, but depending on the specific case, you might have to shift and turn around to always satisfy this property that you separate the sequences from one to one side and the other. Okay? Any question? Can you repeat? The reason is this standard definition of the cross ratios. Because 1, 2 appears here and 1, 4 appears here, so it looks nicer. Otherwise, I would get like u over v and just that. So you can pick any two, and you always get cross ratios, but it can be different than the standard one. Okay. So what should I say now? comments. So first comment is, so crossing symmetry, right? So permutation symmetry of this original correlation function. When you write it in the Mellin language, it's just permutation of this variable. So in particular, for example, here, let's analyze this case. So instead of thinking of this function as a function of two variables, you can think of this function as a function of three variables with a constraint, right? This is like S, T, and U of scattering amplitudes with this constraint here, right? And now it's just like crossing symmetry is just permutation invariance, okay? So this would be crossing symmetry is the function must be invariant under this. So this is, if you want, the first sign that this is very similar to scattering amplitude, okay, at least formally, because the realization of crossing symmetry now is this permutation symmetry between, say, S, T, and U, these three variables that are like Mandelstam invariants, okay? But okay, this is very weak argument, so let me continue to make this analogy with scattering amplitude something more manifest. But actually, before giving you a real physical reason, I want to continue with these weak arguments for one more minute. So I will do something very artificial. So I'll introduce momenta. Okay, some fictitious momenta, one for each particle. And I'm actually a bit afraid of this, but maybe I should call it K, but then I might be confused, but okay. Ki, one per each particle, okay? And I introduce this momenta, and I impose such that their inner product, Ki dot Kj, is given by these Mellin variables, gamma ij variable, okay? So in particular, there is an on-shell condition. So Ki square is minus delta I, right? Because I define gamma ij diagonal like that. So if I do that, then momentum conservation, sum of Ki I from 1 to n equals 0, okay? I introduce this momenta as conserved, implies the constraints on the gamma ij's. Right? So it's automatic, this constraint. So I will think that actually these gamma ij's are really just the inner products of some momenta, which I haven't defined. I only know their inner products, but you will see that thinking of these gamma ij's as inner products of momenta is very useful. Okay? I will convince you of that in the next minutes. Yeah, so in particular for the n equals 4, for the 4-point function, this leads naturally to the introduction of Mandelstam invariants. So for example, I can introduce a variable s, which is minus k1 plus k2 squared, which of course I have to expand, and if I expand, I just get delta 1 plus delta 2 minus 2 gamma 1 2. Okay, some redefinition of what I mean by so I'll just introduce it because it will be useful, but you can think of it just as some trivial change of coordinates. Instead of using gamma 1 2, I can use s. It's some shift. Okay. Any question about this? Okay, now let's do some physics. So why is this Mellin transform good? its nice properties mostly follow from the operator product expansion. In particular, I want to claim that the operator product expansion implies factorization of the Mellin amplitude. So now factorization is what Pedro was telling you that it was a lie, is the fact that you will have poles and the residues are the product of lower point amplitudes. Okay? It seems to be a lie when you have massless particles around because of this physical phenomena of soft emission. But when you have massive particles, which is the best analogy here, it's just true, right? He also was explaining that the poles in the asymmetry corresponds to bound state. So in that context, it's just true. Okay. So let's try to understand that. So what's the best way to do this? Yeah, that's the example there. Very good. So let's look at the simplest example, which makes it pretty clear. So let's take O1. Yes, let's think like this. Yes, O1 at x1 and O2 at x2. And let's take their OPE, so at point x2. So I'll write, so there will be a sum over all primaries, maybe some label Q for primaries. And then there's an OP coefficient, C12Q, the dependence x12 square to the power delta Q minus delta 1 minus delta 2, everything over 2. And then you have the operator, the new primary, OQ at point x2. And this guy comes together with this descendants. And I'll write just one descendant that will be useful for me. x12 square del square of OQ at x2. And there's many more. Okay, so this is descendants. Okay, so now let's try to see what this means for the Mellin amplitude. And actually, yeah, this example will be good. So can you see here? No, maybe not. I'll do it here. So what does the OPE tell us? The OPE is an operator statement, right? It's valid inside any correlation function. So it tells you that in any correlation function, the singularity, like the behavior of the correlator when x12 goes to 0, is controlled by these powers. It's a power-like, and the power is controlled by the dimensions of the operators that appear in the OPE. Okay? So how can we get that from this kind of integral representation of the correlation function? Okay? So from the Mellin amplitude, we get that this O1 of x1, O2 of x2 with whatever is there is what? It's given by, so we're taking the limit x12 square going to 0. So let's focus on that. So you have x12 square to minus gamma 12, right? That's the only factor you get. Remember, sorry, maybe I should remind you. So this is xi minus xj square when you go to the Poincaré path, so the physical RD. And you have this integral d gamma 12 over 2 pi I times all the rest, all the other d gammas and lots of stuff in the Mellin representation. But basically the dependency in x12 is just that, nothing else. Okay. So what is the only way you can get a pure power behavior as predicted from the OP? You have to have a pole, and you have to have a simple pole, right? So in particular, the Mellin amplitude that was here, right? So M must have simple pole add. So let's do it. Gamma 1, 2 equals what? Delta 1 plus delta 2 minus delta q over 2, right? But now, that's why I kept this guy here. Actually, for each primary, you have more powers, okay? So there is x12 square. So this guy increases. So in fact, must have simple pole, sorry, minus 2m, yes, where m runs from 0, 1, 2, all the way up to infinity. So each primary operator, okay, so the statement is each primary operator, so for example, let's do the 4-point function. If you have 1, 2 going to some operator q, 3, 4, so per each primary operator OQ that is being exchanged in this OPE, you will have a pole at this position. Actually, you'll have a semi-infinite sequence of poles at precisely these positions. Okay? And if you assume the CFT as a discrete spectrum, okay, so if you have a discrete spectrum of operator dimensions, then this implies that the Mellin amplitude is meromorphic. It only has simple poles. Okay? You see, if you have a double pole, you'll start to get logs. So that's, well, you can see that in perturbation theory when you start expanding in all those dimensions, but as a non-perturbative statement, Mellin amps should only have simple poles. What else should I say? And of course, I didn't emphasize it, but it's clear also that the residue of this pole is just controlled by the OP coefficients, right? Because you not just have to fix to get the right power, you have to get the right coefficient. So the residue of this pole is controlled by the product of the OPs here and here, okay? So let me write the summary of this result. So more generally, so let's look at the more generally, but still the 4-point function. Because here my argument was simpler because I was just looking at scalar operators. But you can generalize the argument for any operator that is being exchanged in the OPE. Yes?
I'm not sure they can see.
The black hole, right? It's just words, so that's M of S and T. So this should have poles, okay? So this sign means it has a pole in this position with this residue, okay? It just means that. S minus, so the position of the pole is delta Q minus LQ plus 2M. So again, I'm doing this case where the operators 1, 2, 3, 4 are exchanging an operator with dimension delta Q and LQ. Okay, and okay, and again M runs from 0 to 1 and infinity. So the important thing to learn is that you get the twist. If you just do the scalar, you might think that the position of the pole is the dimension. It's actually dimension minus spin. Okay? And then here in the numerator, as I said, is controlled by the product of the OP coefficients. But if the operator has spin, then actually, so this function is a function of two variables. I'm using now this S and T parameterization. So at the pole, you can still have a function of the other variable, t. And what happens is actually what you get here in the numerator is a polynomial of degree given by the spin of the operator, which actually also depends on this little m. But these polynomials, which I will call Mach polynomials because they were first computed by Mach in 2009, yes, when he introduced this Mellin representation. are completely kinematical. Okay, so they just follow from the tensor, the conformal symmetry of this OPE. Okay, so if you now do the OPE with a operator with spin, you get some tensor structures, and when you contract them, you get some tensor structure that then, when it goes here into the Mellin, you can trade that by a specific polynomial. Okay, so this is completely kinematical. There's no dynamics. The dynamics is in the C's and in the dimensions, as usual in a CFT. Yes, it's related to the conformal block. So it's a degree L degree equal to the spin of the operator. Okay? It's related to the conformal block. So in particular, if you take this Mellin representation, okay, and now you just instead of computing the full integral, you just pick up the poles, this entire sequence of poles from m equals 0 up to infinity, and just sum those poles. That's the conformal block. Okay? So the contribution just from the poles is the conformal block. Very good. So here the analogy with scattering amplitude should again be more obvious now, right? Because now you really have an on-shell pole related to the mass of the particle. Remember that my momenta satisfied some kind of on-shell condition where the mass square was this dimension. You should actually think that it's the twist that was for scalars. And so here I'm just seeing that when the internal, so the momenta, if I think here I have momenta k1 and here k2, then here I'll have k1 plus k2. And so when k1 plus k2 square is equal to this internal particle mass, if you want, mass square, you'll have a pole. And moreover, the residue scales as t, the end mass, to the spin, okay, which is also what you see when you have a scattering particle, a scattering amplitude when you exchange a particle of spin L. Okay, this would be in scattering amplitude. This would be like the Legendre polynomial, okay, of the scattering angle. Any question about this?
Yeah. So, is there any particle that has that twist adding the 2m?
Sure. So this is a descendant. So suppose I have my primary. And now I just act with del square to the m. That increases the dimension, but does not increase the spin, and increases the dimension by 2. So increase the twist by 2m. You mean the external particles having spin? I would expect something similar, but that's precisely open question. It's not completely. I'll mention a bit of external spin, but not the general case is not understood yet. You can ask again. Okay, maybe some systematic erasing is necessary now. Okay, we can postpone that. Okay, so what do I want to say? I want to say I want to mention an extension of this result for 4-point functions that we found last year with Emilio and Vasco Gonçalves, which is when you analyze factorization at the level of endpoint functions. Okay, so let's look at an endpoint Mellin amplitude. So I'll put here O1 of P1. Okay, it's still external scalars, but it's many of them. OK of Pk, OK plus 1 of Pk plus 1. Whatever, you see, up to On. Okay, and I have an endpoint Mellin amplitude. Suppose I have that. So now I can also ask what is the contribution? Do I know anything about this Mellin amplitude if I analyze the multiple OPE of all of these external operators? Okay, so I can also consider all of these first K operators inside some sphere in radial quantization and write the entire multiple OPE, and so that should give me also some factorization channel from this point of view. And so that's precisely what we find. We find that if you do this, then the endpoint Mellin amplitude has a pole. So I'll write this variable gamma LR delta Q is the same thing, internal delta. And the residue factorizes into M left, where you have the 1 to K, and here you have the operator OQ times the operator OQ M right K plus 1 up to N. So what is this variable gamma? Okay, so now this is complicated, right? Now it's an endpoint function, so it's not just two variables, there's a huge number of variables, this n minus 3 over 2. So what is this variable that is particularly sensitive to this pole, to this factorization channel? Can you guess? Sum of the dimensions, sum of the k's, exactly. So it's just the momenta that is flowing like the graph suggests. So you sum ki's, well, now that's the problem of changing to k. I from 1 to k, okay? Please don't confuse number of particles with momenta. Squared. Okay? So it's exactly the analog. So these momenta now, I think I'm allowed to introduce them because they really help you find the positions of the poles of the Mellin variable. You just impose this momentum conservation, and the natural on-shell condition that you would associate with this operator, OK, so in this case I'm doing a scalar operator, immediately gives you the position of the pole, and the residue factorizes as it should. Very good. So this is the simple formula. Then there are the more complicated formulas. So more generally, but OK, that I will not write explicitly, but more generally, as you say, this thing will have, first of all, it's the twist when you do generic spin, and as you say, it's a sequence of poles, not just one, with some residues. Let me say Q, or whatever. I already used Q, so let me say residue M. Okay. So the point is that I'm giving you here the explicit formula of the residue for M equals 0 and spin 0. So for higher M, the residue, it's always just a function of the same data. So if you know these lower point Mellin amplitudes, you know the residue, but it's not just a product. Okay, you have to make some shifts and multiply by some gamma functions, so it becomes a bit more messy, the formula. But you can write an explicit formula for the residue in terms just of these two elementary objects. The case with spin is more interesting, because now, if I have spin here in the middle, now this Mellin amplitude has an external leg with spin, and that I have not defined. So let's do it. Questions? So one thing you can see now, you see. So this factorization properties. So if you want to compute an endpoint correlation function, it's a very complicated object. Now we have the hope of trying to understand this object as built from simpler objects just by using these properties as a, so it's a meromorphic function, and the poles and residues are controlled by lower point Mellin amplitude. So you can even imagine there is some recursion relation that you can write down. But okay, this is at the general level of the CFT. Then I will try to show you, maybe I should keep that. Well, let's erase. I will try to show you that in AdS, if you compute Witten diagrams, then really this is the simplest possible form of writing correlation functions that come from Witten diagrams. So if you just write them in position space, you get some special functions with some, well, complicated, mysterious properties. Well, you can try to study them, but they're not transparent at all. If you write it in Mellin space, very simple functions. In particular, like even complicated Witten diagrams can be just constants or polynomials in this language. Sorry? The residues are, sorry. No, they are. Okay, still. They are lower point Mellin amplitudes. Yes, they are on shell. Everything is. Yes, exactly. They are really on shell data. It's like in scattering amplitudes. The pole is a product of two on shell correlation functions. It's just that the higher poles, they are still just a function of on-shell data, but they are not directly the product. It's like you just have to multiply by some factors, do some shift, but it's the same information. You don't have to compute any on-shell information. More questions? So actually, I forgot to say something which is very important. And I hope there's still enough formulas to understand that. So what about the gamma functions? Nobody complained about the gamma functions yet. Why not? So first one comment. The nice factorization formula I wrote only works if I put the gamma functions. Otherwise, I get some extra factors. It's not just like the product of lower point Mellin amplitudes. So the gamma functions help you to have nice factorization property. But they have poles, right? So if you actually do this integral, the gamma functions contribute with terms like the OP. They already have poles, so you'll get some powers of x12 squared. Okay? But the gamma functions have poles at some fixed position. So you look here, you see gamma 1, 2. So in this case, you have double poles because I chose this particular combination. Otherwise, it would always be simple poles. But you see the poles are at the position gamma 1, 2 equals 0. Gamma 1, 2 equals minus 1. And if you map that to S and T variables, so the gamma functions, so poles of gamma 1, 2 correspond, basically they correspond to operators which have dimension delta Q equals delta 1 plus delta 2 plus LQ plus 2M. So what is this? Anyone remembers this formula? It's double trace. Okay. So what happens is that the poles of the gamma functions automatically incorporate the OPE contributions from multi-trace operators. Okay. Exactly. So if you are writing a planar correlation function, okay, in the planar limit, then this is really perfect because you only have contributions. So the Mellin, let me write that. So planar correlators mean that the Mellin amplitude only has poles associated with single trace operators. So that's why Witten diagrams become so simple in Mellin space, because most of the OPE structure inside Witten diagrams is multi-trace contributions. So for planar correlators, this really is a very nice property. Of course, in general, it's not a nice property because you don't expect to have operators precisely with this dimension in generic CFT. So generically, what happens is that if you define it like that, then Mellin will just have zeros that will cancel these poles. Okay, so that's so in that case, maybe it's reasonable to say that you should not define it with this gamma function. You should just define M as the full object. But still, the factorization properties still look nice if you define it like that. So it's really an open question. So for example, if you compute the Mellin amplitude for the 4-point function of, say, the sigma field in the 2D Ising model, you get some nice formula, and what it is, it's 3 gamma functions divided by these 6 gamma functions. So they just cancel. Okay, so they are not there. So okay, that's just the comment I wanted to make.
Why the factorization properties stop in real space?
No, for example, the property that the residue in a 4-point function, the residue is a polynomial of degree L in the variable t, will not be true. You will have some 1 over gamma of t, some shifted, something like that. Just that. True. And it's true, and it provides a factorization. I'm just saying the formula looks nice with the gamma function. If you don't like it, it's okay. You can define a different Mellin amplitude. Yes, it just looks less like it. When you have corrections, no. So even it's what I say here. So if you're computing a planar correlator, so even in planar correlator, sometimes you have it already includes. You can compute corrections, 1 over n squared corrections to the dimension of double trace operators, and that is okay. So the statement is really this one. So if you have a planar correlator, so a 3-level diagram in AdS, then it will only have poles. The Mellin will only have poles associated with single trace. But in that diagram, you can from that diagram you can extract, for example, the leading 1 over n squared anomalous dimensions of double trace operators, for example. Okay, let me then. So the good thing about talking about Mellin amplitudes here is that you already know almost all the technology needed. So what's a vector? So let's consider a correlation function of n scalars and 1 vector operator. Okay, that's something like would appear there that I erased, but I will explain again. Okay, so let's try to guess. No, so it's actually there. So there is for a scalar. So what can we put here? Okay, now we have this this vector index. So we have to come up with a representation similar to the one for scalars, but now that is compatible with this index structure. Well, you have to use one of these vectors, and you should not use p, right? Because that's redundant. So let me just write PA of any one of these points A, and I will sum A from 1 to n. Okay? And now each one of these vectors I can multiply basically by a scalar Mellin amplitude. That would be like the first obvious thing to do. So I'll just integrate the gamma. So there will be a Mellin amplitude with an index A, one for each particle. And then I'll have this product, Pij to the gamma ij. But now, so there's one point which is special here, right? So I'm treating it as a special point. So I'm separating it. So here I'll have that part minus 2p dot pi gamma of something. Okay. So what should I put there in the exponent? Okay. So actually, I think I will just put here gamma I, and I will define it what it is. But if I do it like that, it's not homogeneous. This because here I have weight 1 already in the point A, so I should here add delta IA. Okay, that just means that now the constraints will be all the same independent of A, because the extra weight that I put here in this vector, I canceled with this delta function, so there's an extra p dot pi there. Okay. So we have to play the same game again. So what is the constraints on these variables? What are the constraints? Let's look at pi. So what's the weight at pi? It should be delta I. And what is there? It's sum of gamma ij, j from 1 to n, j different from I, plus gamma I that's what I mean. Sorry, yeah, that's what I mean. Plus delta I, right? And sorry, no. You should correct me, right? It's wrong because I already have weight here, so that cancels the delta function. Okay, so this is weight at point pi. Point pi gives this. Do you agree? Delta I is the dimension of the operator OI, the standard. Right? So what I'm saying is that in this case, since I have a special point, these variables gamma I can be immediately just solved in terms of the gamma ij's. Okay? So that's what this constraint is telling you. But now you also have to satisfy the other constraint on the point P. So this point here, which the weight I'll just call delta, the dimension of this operator I'll call dimension delta. And what do we get on this side? We just get this total sum, right? So we get sum of gamma I from 1 to n, plus 1. Okay, and in fact, so what I want to do is I want to use this, so solve for gamma I as a function of gamma ij, and then the only constraint you have to impose is when you put them together, and let's see, so you just have to sum, and basically it's sum of gamma ij I and j from 1 to n. I think you get delta minus 1 or 1 minus, is it delta minus 1? 1 minus delta. Okay, this is actually, we should not be doing this actually. So the most important point is what goes next. So any question about this? So the point is that it's easy to try this. It's the obvious generalization. There is some constraints on these integration variables. But the main difference is that now instead of having one Mellin amplitude, you have n because there is this tensor structure, so there is n of them. Okay. Because that was redundant. Remember, when you project to the physical space. But there was also a constraint, if you remember. So there was a constraint that vector operators in the embedding had to obey, had to be transverse in some sense. So I've not imposed that constraint, but it's easy to impose them. If you act here with P, you will just get P.PA, and that just will simply cancel this delta function. And basically, right, it's important, sorry. It cancels this delta function, and so you get the right weight without the delta function. But now, to bring everything to the same form, you need to remove the +1 from the gamma function in the numerator, and then you have an homogeneous constraint for the sum of the MAs. So the constraint you get is that actually the sum from A from 1 to n of gamma A times MA has to be 0. Okay? Because you have to put everything together and you get a sum. So it becomes a scalar Mellin amplitude once you contract with PA. And so if you want the full correlator to be 0, the full scalar Mellin amplitude must be 0. But to put everything together, you get this equation. Okay, so with this definition, should I give you something more? So what time is it? No, I should not give you any more details. Very good. So with this definition, you get exactly the right result. So you get a nice generalization. So we go back to this picture where you have a scalar Mellin amplitude from 1 to k plus 1 up to n. You have some scalar Mellin amplitude. And now, if there is a scalar operator being exchanged in the OPE, you have a pole at gamma LR equals delta minus 1, where delta is the dimension of the operator that is being exchanged. And the residue, so you have this lower point Mellin amplitudes, ML, but now with one leg, so they have an A, right? Because they are vector Mellin amplitudes. So here you have the operator OA from 1 to k times, again, another 3-point Mellin amplitude, M right B. Here you have the operator OA again. So the residue is given by this sum over A and B from 1 to n. And here you just put gamma AB. Okay, so now you should think of this as like the sum over elicities that Freddy was writing, right? Now you have a vector operator, so you have to sum over the several possibilities. So here, the best formula we could find was with this definition, you introduce this set of Mellin amplitudes, and then the residue is given by that. But okay, the most important fact is that, again, the residue is completely determined by on-shell data of lower point correlation functions. Okay? Of course, formulas are not as simple as scattering amplitudes, but that it's a fact of life. Okay, I will not say anything else about this. Any question? So let me make some quick remarks then about what happens when you do AdS CFT. So suppose then let's compute the simplest diagrams. So let's compute Witten diagrams, which are just contact Witten diagrams. Okay, some endpoint contact Witten diagram. Okay, so this means endpoint 1, 2, up to n. So I gave you the bulk to boundary propagator. You can write the product of bulk to boundaries propagators, integrate over this point x in AdS, right? Dx in AdS, and that gives you a correlation function. You can write it in the Mellin representation, and what do you get? Any guesses? Sorry? Just a coupling. You just get a constant. Okay, so if there's a coupling constant there, you can put it here. Okay, so that's it. It's the simplest possible Mellin amplitude, corresponds precisely to contact diagrams in AdS. Okay, so this is, well, if you think about scattering amplitudes, that's just what you expect, right? A contact scattering amplitude is just a coupling, right? So you already see that Mellin amplitudes are some kind of amputated, right? It's really like a scattering amplitude. The bulk to boundary propagators don't contribute anything. But then you can continue. So you can start playing with, okay, even here, maybe here I can also. So here, what happens if instead of taking, so this case was an interaction. So I was doing an interaction like phi 1, phi 2, up to phi n, right? So some simple vertex with just a product of scalar fields, okay? So now suppose I take a slightly more general contact interaction where I put derivatives, okay? So I take phi 1 and then some covariant derivatives, contracted, phi 2, and then some covariant derivatives, phi n, okay? And I contract this covariant derivative some way, I don't know, mu, whatever. Some scalar vertex with decorated with derivatives. So what do I get for the Mellin amplitude? So now you go scattering amplitude. Huh? Yeah. If you do scattering amplitude, what would you get? Polynomials, exactly. So you just get a polynomial, and actually the degree is basically the number of derivatives, okay? Or the number of derivatives divided by 2. So polynomial, yeah, okay, I don't need to write. So good, we're very happy. Let's continue. So what happens if I start doing, I don't have space to write the formula I want. What happens if I start doing exchange diagrams? So let me try this one, just to illustrate the features instead of writing. So the point is that we can actually write Feynman rules for, at least for these scalar diagrams, scalar tree-level diagrams in AdS, we can actually write Feynman rules. So let me just illustrate how that works here for this diagram. So the Mellin amplitude. So for this diagram, what would you write for the Mellin amplitude? So what should I say? Yeah, let's say this is particle 1, 2, 3, 4, 5. Okay. So and here these internal propagators, I put some dimension delta, and this one, for example, some dimension delta bar. Okay. Okay. So what would you write? Well, if you're doing flat space, you know what you would write, right? You have to write each vertex. There's some contribution from the vertex and some contribution from the propagators. Okay. So let's just write the propagators here first. So the propagator here, what propagator should it be? Well, you have momentum k1 here, k2 here coming in. All momenta are incoming. So here your momenta k1 plus k2. So this propagator should at least have a denominator, which is k1 plus k2 square with this mass, okay, plus delta. But of course, we know that propagators in AdS are not just one pole. They are a sequence of poles. So you have to put here plus 2m. And there's some numerator that I will not write explicitly, some gamma function that depends on delta and m. But that's your propagator factor. Okay? Of course, at the end, you will have to sum over this m from 0 to infinity. All the poles contribute. Okay, of course, you have another similar propagator, which maybe I can write here. K4 plus K5 squared plus delta bar plus 2m bar S delta bar m bar, for example. M bar equal here. Okay. So what about the vertices? The vertices also depend on the legs that join there, the dimensions of the legs, and they also depend on this internal quantum number, right? So there's an m that goes together and an m bar that goes together. Okay. So there's some vertex that depends on delta m, delta bar, m bar, and what's the other leg? The other leg is delta 3, but it's a bulk to boundary propagator. It's not a bulk to bulk, this one. So m is 0. That's the only rule. Okay? So for example, the other one is just delta 1, 0, delta 2, 0, and delta m. Okay? And I guess you get the picture, no? V. Well, I will not write. So these two functions, these two functions are explicit functions. So they actually, this vertex, it was Miguel Paulos that compute them completely explicitly. And they're just explicit functions. This one is a bit complicated. It's some special function of these labels. But that's it. All the dependence on the Mellin variables, which is really the non-trivial dependence, is explicit here in the propagators. In particular, you see that really the only poles are associated with the internal propagators. Okay? So, I mean, to compute this diagram as integrals in AdS in position space is really beyond the present technology. Well, you can write some integral, but it doesn't tell you anything. Any question? Exactly. Well, I shouldn't say exactly. They are very suggestive of that. There's what is momenta in the bulk. Usually when I give this talk, people ask me, but these momenta live in what space? They are vectors in what space? Here nobody asks me. You guys are sleeping. I don't know why. And I always have to say, I don't know. It's true. I never introduced any space for this momenta. This is really an auxiliary thing. In all formulas, I have inner products. Okay. If you look at this formula, well, it's natural. And another formula that I would like to write, also if I have time, it's natural that these momenta live in d plus 1 dimension, right? Like the dimension of the bulk. But the bulk is curved, so it's not like there's no natural definition of momenta. So.
Sort of like flat space limit.
Right. That was the other formula I wanted to write. How much time do I have? Minus 1 minute. The boss is distracted, so I can continue.
I'm a little bit confused because you're saying that you're getting the same answer as
No, I'm not saying that. No. It has everything to do. It's the same Mellin output. So let's go to the logic. So you have a conformal correlation function object. You can compute whatever you want. You have this conformal correlation function. You can write it in this form, and you have a Mellin output. It's equivalence. It's like Fourier transform. Okay. Now I'm talking about a particular class of correlation functions, which is correlation functions that you compute by doing these Witten diagrams in AdS. Okay. So to a given Witten diagram, there's an associated correlation function, which is given by this integral. Okay. And I'm saying that for these particular correlation functions, the Mellin amplitude is simple. It's like either this or what I was saying there. Is it clear? Now you want a connection to conformal blocks. Okay, now a given correlation function can be expanded in conformal blocks. Okay. For example, this correlation function, let's say 4 point, otherwise it becomes messy. Let's go slowly. This correlation function, what's the expansion in conformal blocks? Not this one, the one with 4. This one. What conformal blocks appear in the expansion of this Witten diagram? No. There are infinite number of conformal blocks associated with the double trace operators of the external operator. Okay? So each Witten diagram contains an infinite set of conformal blocks. So there, this one is richer. So besides all this infinite family of conformal blocks of the multitrace, it also contains conformal blocks associated with the exchanged operators, with the operator dual to the exchanged field. Okay? So yeah.
If I had done a 4 interchanging delta Q, the Mellin amplitudes would have been different.
So this Witten diagram is different from this conformal block.
The Mellin amplitude would not be the same.
No, even don't have to talk about Mellin amplitude. So here if you exchange the operator O, and here you have the dual, so phi is the dual of the operator O. This Witten diagram gives you a correlation function, which is different from this conformal block. So to have an equality, you have to have this plus infinite sums over double trace operators. Okay? Any other question?
Like naively looks like here you define like Mellin amplitude like sum. Then you found some like properties of this amplitude, like they have some poles, they have some like apparent relation or whatever. And then like for me, like there was like this something missing.
Yeah, I didn't explain. This was a statement without explanation.
Yeah, and then why did you write that MF equal to something that?
I don't have time to explain. So actually, the way we derived this, okay. The way we derived this was mostly brute force.
What is the statement?
The statement is that if you compute this diagram in AdS, with usual rules of integrating over vertices, bulk to boundary propagate, all of that, you get some correlator. Then you write it in that form, and the Mellin turns out to be this. Okay? So in the beginning, we did all of these brute force exercises to get this form. Then we understood that there was a simple pattern, that there was some Feynman rules that you could write directly the answer. Okay? But you see, it's actually natural from what I told you, because most of the complication inside this diagram comes from double trace, multi-trace contributions. So since I already argued that the only poles in the Mellin amplitude are single trace operators, then you already know that you should only have this type of poles that I wrote here explicitly. Should not have any other poles. Okay. Then to get these precise factors, you have to go. Well, you could even use factorization to get also these precise factors. So in a way, you can also you can derive these rules using factorization.
What's the relation of this V with bulk coupling?
This V, of course, this V is proportional to the bulk coupling. Here, I'm just saying that it's not just a constant. It depends on this integer and the dimensions. Sorry. Can you speak louder? Sorry, I can.
There's a derivative.
Right. If there are derivative couplings, there's some generalization of this. Right. You will probably, you will get also dependence in the numerator because you are taking derivatives.
We'll talk about like real momentum because you have translation. there, I know the symmetry of this calculation.
No, but it's not exact. So, for example, I guess that will follow from this. No, I can say that that's actually the way I derived the formula I want to write. So, for example, you look at this polynomial. So you write a specific vertex, and then you compute the scattering amplitude in flat space using that vertex, and you also compute this Mellin amplitude in AdS using that vertex. Okay? Given some vertex with derivatives, phi 1, derivatives phi 2, up to phi n, you can compute some scattering amplitude, let's say T, of the Mandelstam invariance. Let's say the momenta in flat space ki dot kj. Okay, so you get some polynomial, right, on these variables. Using this, basically, you just have to contract. Actually, you just have to know how many contractions are between this and this, right? Let's say I have n 1, 2 contractions. Then I'll have here ki contracted with kj to the nij, right? Product overall I, well, let's say less than j. Basically, that's it, right? Given in flat space, computing the scattering amplitude associated with such a vertex, you just transform derivatives into momenta. That's what you were saying. So now, let's see what happens. So this is flat, and this is AdS. So let's see what happens to the Mellin, which is now a function of gamma ij. What happens is that you get precisely the same factor, gamma ij to the nij, plus subleading. By subleading, I mean terms which don't, so the maximal power here is, right, n is equal to sum of nij. So this is like gamma to the n minus 1, things like that. Okay? Order gamma to the n minus 1. Okay? So it's not true that you can just replace derivatives by momenta. But the leading order term of the polynomial, indeed, is exactly the same as in flat space. There is, yeah. Actually, there's some function here that depends on n. If you put here some coupling constant g, like here g, you get g. But now there's some function that depends on the number of derivatives. That's why the formula I'm going to write right now, I really have to write it. It's not as simple as it should. So, should I write it or should it's distracted? Very good. So I'll write. Okay, so what is this formula? This formula is for the following. Let's take, it's precisely this experiment that I was describing there. Let's take flat space. So let me just draw like some kind of diamond to describe flat space. And let's take some Witten diagram here. Sorry, some Feynman diagram here. And you describe some scattering here. So there's some scattering amplitude T of this momenta. Ki, okay, it's a function of Mandelstam invariance. Ki dot kj, like I was describing there. So in particular, it could be a contact interaction. Okay, and now let's draw exactly the same Feynman diagram in AdS. So it becomes a Witten diagram. So the only thing that changes is that you integrate over AdS, and the external legs, instead of being plane waves, are bulk to boundary propagators. Okay, just that. So here you have a Mellin amplitude. So what you can do is to write a formula that relates the Mellin amplitude you have here, which is now a function of the gamma ij variable, with this scattering amplitude. And so I'll just write the formula, and then we can discuss in the afternoon. So you take your gamma ij, and what do you do? Well, it's already coming from that expression. You want to match leading terms, so you want to take gamma ij to be very large. So the natural thing is to write ki.kj, and then this is dimensionless, so you have to multiply by r squared. And so, of course, the limit has to be a limit when r goes to infinity, right? Because you want to go from a curved space-time with radius of curvature r to flat space-time, so the radius should go to infinity. And so this is giving you what you want. But to get a precise formula, you have to actually introduce some auxiliary variable alpha, and there's some integral you have to do over alpha. Alpha to some number. It's sum of dimensions, I think. D minus sum of dimensions over 2. Yes, okay. There's some constant. You don't need to know about this constant. That's it. Okay, so actually it was good that you asked me this question, because what this formula does is basically apply to this specific case. You see, you already get the leading order term. So if it's polynomial, the limit r goes to infinity just picks the leading order term in the polynomial. So that integral just creates this function that depends on the number of derivatives, such that you can apply the same formula to whatever vertex without having to know a priori with the number of derivatives. Okay? So that formula just does this game of going from here to here for all possible contact interactions. That's what she was tailored to do. She was created to do that. That's what this integral does. Okay? And okay, now the argument is that this is a true formula, because you see, this is a complete basis. Any interaction, if you expand with arbitrary number of derivatives, you can write any possible interaction in this form. And well, in particular, you can also test this in many examples. You can test this formula by computing other diagrams, exchange diagrams like I was drawing there, and you check that it also works. And actually, there's a different kind of derivation of this formula by Jared Kaplan and Liam Fitzpatrick, which really, what they do is to really construct scattering inside de Sitter space, but scattering of wave packets. So they prepare wave packets coming in from the boundary such that they only scatter in a small region inside AdS, much smaller than the radius of curvature. Okay? So by doing that, they can really extract the flat space S matrix by this wave packet construction, and they get to the same formula. Okay? So this is another indication that these gamma ij are really something like the bulk moment, the inner product of bulk momenta, but okay, that's the concrete formula you can write. Sorry for going over time. Thank you. Yeah, we should probably go for lunch and continue at 2 with the discussion.
Can you bootstrap these Mellin amplitudes and spin the correlation functions? Does that actually buy you anything?
So far, we couldn't make any progress in that direction. So we tried a bit, but it's not clear. It's not clear. Mm-hmm. It looks good,
yeah,
right?
Because you know all this additional information.
Yeah. But yeah, convergence. I think there's a problem with convergence. You see, the OPE, the bootstrap works very well because the OPE is very fastly converged.